Another common functional programming technique is called accumulators. So the idea here is to capture the common pattern when you're accumulating values into a variable like a sum. So you can, for example, have sum equals sum plus A, sum equals sum plus B, and so on. This is something that we do all the time in regular programming. But there's a problem here with functional programming because the value of sum keeps changing, whereas in functional programming we want the variable to have an immutable value, to not change once it's been assigned. So what functional programmers will do is introduce an accumulator. So they will have an accumulator A1, which will be set to 0, and A2 will, and I'll just make it an add operation, will sum, let's say, A into A1. A3 will add B to A2, and so on. So now you have different variables and you have new accumulators so that the value of each accumulator is immutable, whether it's A1, A2, or A3. Now in object-oriented programming, the way we capture accumulators is with an accumulator object. So there what we will do is we will do A dot put, say some values you're adding X, A dot put Y, and then later on when you do a get, this will return the sum of X plus Y. What we would like to do is somehow combine the benefits of accumulator objects with functional programming and use them for parallelism. And the idea over here would be that you want these add operations perhaps to go in parallel. They may not be integer adds, they may be more expensive operations on matrices or larger objects. So let's say you have an async for an add. So what we would do is allocate a new accumulator and put the values in the accumulator just like we do in the object-oriented case. We put X, we put Y, but the interesting thing in this case is if these are running asynchronously in parallel and we want to do a get, we may not be sure what value we would receive because the puts may not have completed for X and Y. So as you know, what we normally do over here is do a finish, which ensures that these puts have been completed before the get. But for accumulators, what we can do is register the accumulator with the finish. And now this accumulator is associated with the given finish, and when we do a get, we are guaranteed that we'll get the value after all the tasks have completed. A very interesting example is one we've seen earlier, is matching a pattern in a string. So if we have an array of text 0 to n minus 1 and a pattern of length m, to search for the occurrence of the pattern in the text, we can have these two loops for I going from 0 to n minus m, and for j going from 0 to m minus 1, and then you check if text of I plus j is equal to the pattern sub j. And if we want to keep track of the count of occurrences, we can say if so, we can do a put in an accumulator of 1. And then when we are done, the accumulator will give us the total count of all occurrences of the matches. Now what's interesting is if we put an async over here, All these matches for different positions in the text can go in parallel. And then we have a finish with the accumulator registered on the finish. And when we are done, we will get the count of all occurrences of the pattern of the text, and the answer will be the same because the accumulator is performing an operation that's commutative and associative. So regardless of the order of the puts, you will always get the final answer. So what we've seen is that a common paradigm in functional programming is accumulators for performing associative and commutative operations, and they lend themselves to parallelism by being associated with the finished scope so that you can get their benefit in parallel programming too.